Hi folks, this is Professor Schwitkus, and now we're going to be talking about the formation of the solar system. We've just spoken about various things in the solar system, as indicated in this chart, what the solar system is sort of coarsely made out of. And part of this is I want you to take a look at this link here, particularly, let's actually go to it. This is a link for the Planet series by the BBC, and this is something I would like you to look at. So you just click on the link, go to it, and basically you're going to see this sort of thing pop up, and after a while you can look at various things, and in conjunction with watching this video, what I'd like you to do is to answer the questions that are part of the planets and the Don Pettit video worksheet. So make sure that you have a copy of that worksheet with you and can copy down the answers and then transfer them onto etudes so that they can be assessed. Okay, so let's continue on. We talked about classifications of the planets, and I want to remind you that that's how we're going to figure out how the solar system is formed. We need to first of all characterize what these planets and the sun is, and what characterize the pieces of the solar system. That's what we naturally do, and from that we can figure out how it gets created. Okay, so what are the properties of the solar system that we're going to have to explain? Here's a whole listing of them. Some of the largest ones, as you'll find out in the planets movie, is the direction and the motions of the planets about the sun. That was the key thing that Swedenborg and Laplace and Kant utilized to come up with their theory. Since then, we have these other essences of the solar system, and we can explain what's going on. Okay, first thing is first. The sun and everything that is in the solar system are made from the same stuff. That's what this chart shows, except for those elements that are being created in the sun through fusion. Now, we're going to be talking about fusion and that process a little bit later when we talk about the sun exclusively. But if we exclude these three elements, and naturally hydrogen and helium, and we look at the elemental content of asteroids with those of the sun, we find that they line up almost exactly, that there are equal percentages of elemental content in either the sun or the rocks of the asteroids. Basically, if I give you a rock, you can't tell where it came from. It's pretty interesting. So the solar system is made of all the same stuff. Very curious indeed. Now, what the solar system has to explain and the clues associated with the solar system sort of go hand in hand. Basically, all the planets revolve in one direction. All the planets rotate about their axes as they revolve about the sun, except for Uranus and Venus. So we're going to have to keep track of these exceptions, though. All the planets are in the same orbital plane. We call that the ecliptic. Their composition, the heavier stuff is closer to the sun, the lighter stuff is further away. Basically, you guys probably already know that Jupiter and Saturn are gas giants, and that the Earth is not made out of gas, but mostly made out of rocks and stuff like that. So that's what we're talking about, heavier stuff closer to the sun, lighter stuff further away. There are these notable exceptions. We talked about Uranus rotating about its axis in a different way than the rest of the planets. But we also have another exception, which is basically our moon. Except for Pluto, and some other entities out there in the Kuiper Belt. Basically planetoids that are associated with Pluto. There are no moons that are nearly the same size as the planet. Okay, the moon is about a fourth to a third the size of the Earth. And for the terrestrial planets, that is kind of an oddball. Mars is the only other planet of the terrestrial planets, the four guys up front, that has any moons. And those moons about Mars are quite small, about the size of the comet or asteroid that knocked out the dinosaurs. I mean, it's, a few kilometers wide, maybe 10, something of that order. But the moon is, much, much larger than that. Okay, so let's continue. There are two theories that come to mind, at least come to my mind, in regards to the formation of the solar system. One was taught during the 1950s and 60s, and this is what I grew up with. Basically, the sun was approached by another star, and that star tore away material from the sun, and from that debris, planets were formed. One would expect that these planets would be coming off in all sorts of different directions, because that's how, that's sort of the reaction you would expect by a collision that's sort of random. Now, as the Planets movie shows or talks about, they talk about Quentin Laplace coming up with this proposal called the nebular hypothesis. Actually, it was preceded, or the person that really came up with this idea was Swedenborg from, as you might guess, Sweden. The idea is that the solar system formed from a giant gas cloud and collapsed out somehow. Well, I say somehow, because there are a number of ways that it can collapse in general. For us, it's thought that a supernova blew up and caused this cloud to collapse. But there are typically three ways that this can happen, that we can see evidence for in the sky. Let's continue. The formation of the solar system basically can be described in one chart. It's pretty simple. We have a big gas cloud, and somehow it collapses. Now, the somehow is basically supernova comes by and smacks it. We could also have the situation that is taking place in the stellar nursery, that's the Orion Nebula, where bright stars are pushing against a cloud, and therefore it would cause a collapse of that cloud. When the cloud starts collapsing, it will tend to get smaller and smaller, and as it gets smaller and smaller, then it's going to speed up in rotation and it's going to flatten out. This is a natural process. The way I like to explain it is, imagine that you're in an amusement ride, where you're in the amusement in a bumper car ride. The last one I was at was over at let's see, what is the one out in Anaheim? Not Disneyland, but the other one. Well, at any rate, so it'll come to me when I least expect it. But anyway, so you're in bumper cars, and in the beginning, I don't know about you, but I like to go against the grain. And so, in the very beginning, you're bouncing off of everybody. And everybody is going in every which way. Now, after a while, people have a tendency to get tired and to orchestrate their emotions with other people so that they don't get bumped so much. Now, I'm the outlier. The last time I was there, I continued to go against the grain. But at any rate, the idea is that natural processes are the same, and whether or not you believe that we're a natural organism or not, we have these tendencies too. And the example of the bumper cars is really a good one. You start to just rotate in the same direction as all these things, and the actual motions sort of tend to average themselves out, and basically you're going round and round and round. The next step in the process is, as the collapse continues, especially in the center where the protostar or the protosun is going to occur, there's going to be a temperature gradient between the center and the outside. It's going to be hotter in the inside and cooler on the outside. And that's generally caused because in the center there is more material, it's denser, and when things become more dense, they become hotter. An example for this situation is the last time, if you pumped up a bicycle tire, if you put your fingers around the nipple where you're pumping in the air, that gets really, really hot. And that's what's going on, because that's what's going on in the solar system here, in this proto-solar system, is the same thing. As the region gets denser, it gets hotter. Sort of, the explanation we had of what temperature meant. If you have more particles that are closer together, they have a tendency to move around faster, certainly relative to each other. And so if you want to try it out, get a bicycle tire and a pump and pump it up and see what happens. You'll see that I'm actually right in this case. So what ends up happening in this case is the region close to the star or the protostar is now going to have gases of water, and outside of what is called a frost line, there will be ices. So water ice, for example. Because of these materials, we can also have from the sun some radiation taking place and causing electromagnetism, causing static electricity to occur. And when we have static electricity, and you saw in the Don Pettit movie, that with static electricity you can have things collect, we can have condensation occur, and various other mechanisms that start pulling together the particles that are like the fine dust in the fine cigarette dust that Hal Levinson was talking about in the Planets movie. So after a while, we can sort of start creating more and more heavier objects, and gravity will take over. Okay. The next step is basically the sun turns on, the light from the sun becomes more powerful, and it drives the dust and the gases away. It has a tendency to do that less as you get further out, and especially for those regions interior to the frost line, you're going to have a very empty region, and basically you're only going to have planetoids left, and then you're going to have the accretion and the planetary bombardment that has been talked about. So in the interior region where you had 100 planetoids, and now you have 4 planets. Now on the outside, it's not entirely clear what happened, although we'll see that in this region here, we probably had 4 or 5 very, very large planets that were all trying to grab as much material as possible, and basically Jupiter won the race. And then because of the excess material out here, there were interactions, gravitational interactions between the planets and these objects out here, which caused Uranus and Neptune to move out, as well as Saturn and Jupiter to move in. Okay, and that's essentially what we have left. The motions of these particles ended up creating the Kuiper belt and the Oort cloud out here by those planets just spewing this material out. Okay, so let's pause here for a moment. Okay, so here is a visualization of what I've been talking about.
This animation begins by looking at a very massive star late in life. At death, it explodes as a supernova, expelling matter outward and causing shock waves to impact nearby interstellar clouds. This act of violence triggers the birth of new stars, one of which is our Sun some 5 billion years ago. Early on, the formative solar system flattens into a disk, with the forming Sun at its center. Eventually, the planets begin to form by accreting matter that has not yet fallen into the Sun. Afterwards, the Sun's radiation and bipolar jets sweep away debris. Now, some 1 billion years after the solar system formed, 9 planets are mostly identifiable as worlds in their own right. As we continue zooming out, we encounter a few loose meteoroids in the asteroid belt midway between Mars and Jupiter, but mostly there are many more rocks and debris in the Kuiper belt beyond Neptune. Finally, we pass through the huge Oort cloud of comets swarming around the outer edge of the solar system, nearly a light year away.
All right, one of the things that you may have heard of late is that folks are thinking that there are indications of a ninth planet that is out in the middle of the Oort cloud someplace. It hasn't been observed yet, but they have certainly are predicting it to be there. So that's a possibility, and that would give a lot of credence to this this theory that we're talking about now. Okay, so let's pause again, and we'll say I think that I got this situation under control a little bit. So here we're going to take a look at a simulation showing a cloud collapse. Now, what you're going to this is kind of an interesting movie. So we're going to be looking at, in the beginning, just a big spherical cloud, and then we're going to just watch it collapse of its own accord and see the creation of a whole bunch of stars and perhaps a solar system or so. Okay, here we go. So notice the bright yellow spots. These are regions which are more dense than others. And it's no longer spherically symmetric. It's no longer like a ball. It's, little tendrils and things like that. Now we're changing the density scale because there are certain regions that are no longer, sparsely populated, and it's now a lot more dense. And now we're going to jump into this region here. And then of that region, we're going to pick out, probably there, take a look at what's going on there. And we see one down here as well. But notice all these stars are being created and then also being thrown out. It turns out to be very difficult to have a number of objects that are roughly the same size orbit each other. So the solar system is pretty stationary and stable, but if you had multiple star system, that's sort of out of the ordinary, that they're all relatively close to each other and spinning around each other. If you have a bunch of big stars and then something very far away, that's a different situation. It's more stable. Now there's a simulation called Super Planet Crash, which is something that you can play with on your own. Maybe we can take a look at it in a little bit. But the idea there is, you can see firsthand that it's very difficult to get a solar system that has roughly planets of the same size as the star to to stay around for any length of time. Look at all these stars being created. Just amazing. And now we're going to pop out and see what's going on with the rest of this cloud. And basically what you see is, here's the region that we're concentrating on, but there are other regions as well, and look at all the stars that are populated just all over the place. Okay, that's where we started. Okay, cool. Okay, so we've seen what the simulation shows us. If indeed this is a natural process and it's not unique to our solar system, then we should be seeing it all over the place. And I get to report to you that we do. There are some special ones that are close by that are really neat to look at. For example, the Orion Nebula, or the Pillars of Creation in the Eagle Nebula. Both of those are good examples. The Orion Nebula is something that you can see with your naked eye, although it is much more spectacular using a telescope, as you can see here with the Hubble Space Telescope. Basically, we see the evidence of a star and disks around it. Pretty amazing stuff. Here is another picture of the Orion's sword, or the Orion Nebula. This region here is a set of stars called the trapezium. There are 4 stars, as you might guess from the word, that looks like trapezoid, and they're over here as well. This is an infrared photograph, and this is a visible one. And the idea I want to get across here is with the infrared observations, we can look through the dust and the clouds, if you will, the smog of the nebula, and we can see the creation of new stars. And that's what we see over here. Look at all those stars all over the place. Here's another picture of the same thing. Again, this is in the visible spectrum, and this is in the ultraviolet. These are false color images. And when I originally looked at this, I basically was looking at this and saying, this has got to be the infrared because I see more stars here. But I've since gone back to the APOD link, the Astronomy Picture of the Day. And what you should be looking at is see all the darks, all the little pinpoints here, and you just don't see them down there. That's the key thing. And here are some more pictures showing evidence of disks around stars, just, and jets popping off as well. And that's what we expect to have happen. Some more pictures about seeing stellar, or seeing disks, nebula disks around stars. Pretty amazing stuff. Okay, we'll pause here, and we'll pick it up soon.